Hello, today we're going to be going over the methods and results of our signal identification lab. Our team members include Joseph Janine, Ryan Huo, Walter King, and Nicholas Swach. Our group number is D11. We'll begin with a discussion of the objectives and methods utilized during this lab. Then we'll discuss the results from the system nonlinearity, time domain system identification, and frequency domain system identification portions of this lab, and end off with our overall conclusions. In this lab, our objectives included modeling a brushless DC motor and identifying the bounds of the nonlinearities present in the system, including dead zones and saturation limits. We also wanted to characterize the DC motor to understand how the frequency responds to different voltage inputs. Finally, we wanted to model a step response for the robotic arm that would effectively operate in an automotive industrial plant. There were two cases that we wanted to investigate.
The experimental setup for this lab consists of a DC motor and the support equipment necessary to control and observe it. The DC motor is connected to the DC motor board, which receives commands from the myRIO. The myRIO, in turn, is connected to the computer. The computer also receives inputs from the DAC, the data acquisition board, which is observing the optical encoder on the rear of the motor. Using this experimental setup, we're able to both control the motor with a variety of input signals as well as observe the motor's response to those signals.
Now let's talk about the voltage versus steady-state frequency. In the left image, we've indicated the dead zone, linear region, and saturation region. And on the right, we've zoomed in on the dead zone region to more clearly indicate where the bounds occur, which is between 0.1 and 0.2 volts. The linear region is found between 0.2 and 6 volts, and lastly, the saturation region is between 6 and 10 volts. We've indicated the dead zone to be within these bounds because the angular frequency at this set voltage is near zero, and it does not increase linearly with voltage. As for the saturation region, the angular frequency levels off and is also not influenced by the increase in voltage. So what is the purpose of defining the saturation and dead zone limits? Well, we are able to define the bounds of the linear region, which enables us to obtain the motor gain constant Km, which equals 9.107. And this was done by simply dividing the angular frequency at steady state by the input voltage, or simply finding the slope of the red line. The effects of the dead zone and saturation zone on the motor operation. First, the precision within the dead zone and saturation zone in terms of motor position will be hard to predict because the motor may not respond to voltage inputs due to irreversibilities. The motor will not spin in the dead zone region despite being given a small voltage. Within the saturation region, the motor will no longer increase in steady state frequency in response to an increase in voltage.
The purpose of this segment of the lab is to utilize a step voltage input to solve for the theoretical and experimental motor constant and settling time. The settling time was solved for using a numerical method to find the start of the steady-state region, where the average of the following four frequency values were equivalent to the previous iteration's value. The experimental values for the motor constant at various input voltages were found by dividing the frequency by input voltage at a point where the time is equivalent to the settling time. From the plots illustrating the relationship between input voltage and the motor constant and settling time in the linear region of the frequency plot, we can see that the motor constant increases with the horizontal asymptote at 9.05 revolutions per second volt. After approximately 2 volts of input, the motor constant changes minimally. The time constant remains relatively constant regardless of the voltage input. It is expected that both these values would typically be constant over the voltage range. Clearly, this is not the case. The likely reasons can be boiled down to general irreversibilities in the motor system, like friction and internal resistance.
The figure on the left shows the theoretical frequency versus time curves for a number of input voltages. These curves were obtained from the theoretical model at the bottom of the slide using the Km and Tm values previously obtained for various input voltages. We observed that the steady-state frequencies predicted by the model are near identical to the nominal experimental steady-state frequencies that we observe. However, zooming in on the experimental steady-state responses, it is seen that the steady-state frequencies do fluctuate. The fluctuations are not large, and they are centered around the nominal steady-state frequency, but they are present for all voltages over the entire domain of time. Several assumptions were made in the derivation of the model. Friction was assumed to be negligible, and motor inductance was ignored. The effects of these on model parameters, and perhaps others, lead to steady-state frequencies that are not perfectly constant.
Composite values for the two constants, motor and settling time, were found to be 9.0064 and 0.234 seconds, respectively, for the system with the mass. For the system without the mass, the motor constant remains relatively constant, while the settling time actually decreases to 0.176 seconds. Because Km is a function of input voltage and steady-state frequency, there is no notable difference between the Km values for the motor with a mass and without. On the other hand, when a mass is added to the motor's settling time increases by 0.58 seconds, which is expected because the settling time is dependent on the mass moment of inertia of the rotating components.
For the frequency domain analysis, we recorded the input voltage of a sine wave with a 1 volt amplitude, and then we recorded the output voltages of the output signal. And we did this for 15 frequencies ranging from 0.1 Hertz all the way to 10 Hertz. For each frequency, we were able to find the output amplitude, input amplitude, and change in time between voltage peaks using MATLAB. With this information, we were able to find the phase lag as well as the gain with the formulas on screen. Some trends we experienced were as frequency increased, gain decreased while the phase lag increased. And based off the formulas derived from the first order transfer function, these trends seem to make sense. Having found that data, we were able to convert frequency from hertz to frequency in radians per second, as well as find magnitude in decibels. We then fitted this data of magnitude versus frequency and phase versus frequency with a fifth order polynomial using the polyfit function in MATLAB. And from this, we were able to find the 3 decibel point, and we were able to find the cutoff frequency. And with this cutoff frequency, we were able to find the motor gain constant as well as the motor time constant. We see that the motor time and gain constant in the frequency domain are similar to those found in the time domain. Plugging them into the first order transfer function gives the displayed mode plot. The theoretical diagram seems to match our experimental data, verifying that a first order system is valid. We see that frequency domain is useful for analyzing the system as a function of frequency and also verifying the degree of the transfer function.
It is important to use an appropriate method to obtain Km and Tm. For use case 1, either the frequency or the time domain method is acceptable. The voltage is in the linear range and the frequency of 0.1 Hz is in the constant gain region and below the cutoff frequency. However, for case 2, only the frequency method is acceptable. The time domain cannot model the gain attenuation that occurs at frequencies higher than the cutoff frequency. Because the time domain method does not consider frequency, it is not appropriate for use case 2. This concludes our presentation. Thank you for your attention, and we'll be happy to discuss any questions that you might have.